Hello, chemistry students. Again, I'm not in class, so I wanted to go through a little bit of a lab introduction for you. Tomorrow we're going to do our spectroscopy lab, and I've already had you watch a number of videos on spectroscopy, what it is, what's actually happening when you hold up that spectroscope to a flame. And so tomorrow we're going to perform our lab, and I just wanted to give you the opportunity to kind of practice and work ahead on your lab handout. So what we're looking at here is the lab handout called Spectroscopy, a Hot Lab. And you guys can read this whole introduction on your own, but I just want to come back down to this diagram that we have here. And so our directions are to draw an electron on the diagram to the right that has moved from its ground state to an excited state and then back to its ground state. So I'm going to go ahead and do just that. I'm going to pick a color here for my electron. I guess I'll pick this bright blue. And so I'm going to say that my electron is starting off here at the very lowest energy level. And now it's moving up to an excited state. And now it's moving back down to its ground state. And so it's going to come right back down because remember, what goes up must come down. It says indicate where the electron has absorbed energy with a green star and where it has released energy with a red arrow. Well, in order for an electron to move up to a higher energy level, it must absorb energy. So our energy absorption will be indicated with a green star. That is what is happening right here. So when the electron absorbs energy, then it's going to jump up to a higher energy level. And then when my electron falls back down, the only way for it to fall back down is to lose the energy that it just gained. So, shoom, there it goes. The energy is leaving, and my electron is falling back down to its ground state. When the energy is released from the electron, when the energy is releasing that energy, that is when different wavelengths of light are emitted. When the electrons fall back to their ground state, that is when you see the lines in the discrete spectrum inside of the spectroscope. That's what's creating the emission spectrum. So what you guys have to do then is I would like you to please read these directions. And you're not going to perform all of this today, but I just want you to be ready for what you need to do. Since we are using open flame, those of you that have long hair, be prepared with a hair tie to pull that hair back and try to be cognizant of what you're wearing tomorrow. You know, nothing too loose or too flowy. Because again, we are working with flames and I just don't want any accidents to occur over the Bunsen burner. So let's scroll down a little bit. The next thing that you're going to do is grab a spectroscope from the back in a minute after I finish this video for you. And I would like you to look through the narrow end and point the wide end straight up at the ceiling so that through the little slit on the wide end, you can see the white light from the fluorescent lamps in the ceiling through that little tiny slit. And what I would like you to do is with markers or with colored pencils, I would like you to duplicate what you see inside of the spectroscope. Now, if you look at our scale here, you'll see that I have some different measurements. 700 nanometers, 600 nanometers, 500, and 400. The light that has the smallest wavelength would have to go on the 400 nanometer side, while light that has the larger or longer wavelength would have to be over here at the 600 and 700 nanometer side. So that being said, from prior videos that you guys should have watched, you should know that I'm going to change my color here, that over on the 400 nanometer side, you would have your violet light. Whoops, wrong color. Let me change my color. There we go. So our violet light would be closer over here to 400. So I would draw a purple line close to that side, whereas my red would be, I think if I remember correctly, it's going to be a little bit closer to about my 600 nanometer side, right about here. But again, you should be recording what you see in the spectroscope, so it might be different from what I am actually remembering here. And then you're going to have all of the other colors in the visible spectrum ranging from about 600 down to about 400. So again, just make sure that you're actually drawing what you see in your spectroscope when you are pointing it up to the white light. Now, tomorrow, what we're going to do is I'll have 6 Bunsen burners set up, one on each lab station, and you and your partners are going to travel from one lab station to the next. And it's going to be very orderly. I'll turn the lights on and off and things like that. But basically, what you're going to do is take a wooden stick that's been soaking in water. You're going to dip it into a beaker that contains powdered metal ions, and you're going to burn it in the Bunsen burner. And while someone is holding the stick and burning it, another partner looks at that colored flame through the spectroscope. And you not only have to record the metal ion, so I know that one of them, for instance, is calcium, but then you also have to record the flame color. So if you think that the flame color looks yellow, then you would write yellow here. Now, I don't want you to just draw a line for yellow on your spectrograph results. You have to look through the spectroscope at the flame, and just like you do with the white light, you have to draw all of the colors that you see in the spectroscope. So if you see red with calcium, then you need to use your white light as a guide and draw a red line directly under it. If you see orange light as well, you might draw a line here close to the 600 nanometer mark. And maybe you see a little bit of green, and then you would put it wherever the green number is. Again, always referring back to your white light spectrum for, as a guide. For some of you, it might be easier for the person who's using the spectroscope, instead of trying to color when the lights are off, maybe the person with the spectroscope should just call out the color lines that they see. So if they see red, orange, green, instead of taking the time to try, instead of taking the time to try and draw that here, you can just write red, orange, green on your page. And I can make 2 copies of this lab for everybody, so that the page that you're using during your lab is actually your scratch paper, and then you can transfer that to your good lab later on. So anyway, you're going to do this, so then later you can go back and say, okay, we saw red light, so I'm going to go back and pick my red color, and I'm going to put my red here, and my green over where green is, and then orange wherever orange ought to be, and then you can erase this portion. So that's how you're going to do all of the little graphs that you have on this page. But if you go all the way to the bottom, you'll notice that we have an unknown. So each lab station is going to receive a vial that has a mystery number on it. You need to write the number here above the unknown. So here's your mystery number. Tell me what the color of the flame was. And then you have to add the spectrum. Now, your unknown is going to be one of the ones that you've already tested. And so what I want you to do is to provide evidence. So why do you think your unknown is copper, or why do you think your unknown is strontium? So you have to tell me why you think that is. Support your claim with evidence from the lab. So if we move on down, you're going to see that you have a couple of questions that you'll have to answer after the lab is done. I know that for my group, I'm going to omit number 4. You won't have to do that. But this is a part here that you could probably do today before you leave. So again, read these directions. And I just wanted to show you really quickly how to figure out what elements are in star A and what elements are found in star B. So why don't we look at star A first? You'll see that I have the emission spectrograph for star A, and below it I have the known spectrographs for a number of different elements. And what you have to do is match the lines in star A with the lines that are in the element. So for instance, if I first look at Mercury, I can already tell that in star A, I am missing this first spectral line for Mercury. It's not there, it's missing. So since I have a spectral line missing for Mercury, I know that Mercury is not in star A. But let's look at strontium. For strontium, it looks like I've got the first spectral line, like here, but just like in Mercury, I don't have the second one. So since I don't have all the lines, that means that strontium is not in A. Looking at sodium, my first spectral line for for calcium is not in A either, so I know that calcium is not there. And here I've got sodium, and sodium looks like it's a little bit off. So I'm going to say no to sodium. But if I look at helium, you'll see that I've got all spectral lines for helium match up with star A. So helium is definitely in star A. And then you would have to check for hydrogen and see if it is in there. So then you just have to list which elements make up star A and which ones make up star B. So I just did star A with you. You can figure out star B. Real quick before I run out of time, I just want to review what I would like you to do today in class. Number 1, please read this first page of Spectroscopy, a Hot Lab. Fill out your electron diagram here. Read the directions. And please use the spectroscopes that are at the back of the room to complete the white light spectrum. So that should be done before class tomorrow. And finally, don't do those questions yet. Omit number 4. And finally, when you come down here, I'd like you to please do this last page. figure out which elements are in star A and which are in star